All right, let's just jump right into this one. What if an AI system could do more than just remember stuff? What if it could look back at its own history, critique it, and even correct it? Today, we're going to dig into a paper that's all about that. A memory system so good they used it to test itself.
This right here, this line from the brief, it sums up the whole project perfectly. A team of AI agents was built, they were given this new memory system, and then that same team, using that same system, went on to design and run the experiments to see if it even worked. It's this wild recursive loop.
And this is where the rabbit hole gets really deep. I know, this quote is a bit of a mouthful, but you gotta wrap your head around it to see how wild this is. The system was so effective that it actually remembered a mistake, an overclaim, that the agents made in an earlier draft of the paper. In the process of them finding and fixing that error, that became part of the data for the final paper. The system literally documented its own flaws. It's incredible.
So, how did this all start? Well, like a lot of great innovations, this one kicked off with a very real and apparently very frustrating problem.
This slide just nails it. The creators had this team of specialized AI agents, right? One for infrastructure, one for marketing, the whole deal. And they were brilliant at their own jobs, but they had zero collective memory. They were basically a team of amnesiacs.
I mean, can you imagine showing up to a meeting where nobody remembers any of the decisions from the last one? That was the reality here. The marketing agent had no idea what the infrastructure agent just built. The design agent would forget its own rules from one day to the next. They desperately needed a way to build a shared history, some kind of institutional knowledge.
And that leads us to the solution, which they cheekily called Poor Man's Memory, or PMM. And let me tell you, it is deceptively simple, but wow, is it powerful.
Okay, so at its core, this is a huge shift in thinking. See, most AI systems use something called RAG, where information is just kind of automatically found and pushed to the AI. That's infrastructure-led. PMM flips that on its head. It's agent-led. It gives the agent the tools and a map, and the agent has to actively go look for the info it needs. You know, it's a difference between being fed and knowing how to cook for yourself.
And this is the beautiful, simple core of PMM. It's not some fancy, expensive vector database. It's just a set of structured markdown files tracked in Git. That's it. You've got a file for decisions, one for lessons learned, one for standard procedures. The structure is the index. The agent just knows, hey, I need a past decision. I'll go look in decisions.md. It's simple, you can audit it, and it just works.
But, you know, saying something works is one thing. Proving it, that's a whole other story. So the team designed this really tough experiment, a gauntlet really, to test just how well this new memory system actually performed.
To prove it, they set up 5 different test groups. Let's walk through them. First up, the base arm. No memory, total blank slate. Then you've got the on arm, where the memory files were there, but the agent wasn't told about them. Kind of like a scavenger hunt. Next, Stew and Stew Plus got the entire memory bank stuffed into their context. The key difference is that Stew Plus also got the file structure. That made it the oracle, basically the perfect score, the theoretical best you could do. And finally, you have our PMM arm, which just got a small sample of recent memories and the tools to go find the rest. And remember this, every single agent had access to the exact same information. The only thing that changed was how they got it.
So how do you even measure success here? They came up with this really smart metric called the retrieval to oracle gap. It's just a fancy way of asking, how much performance do you lose by making an agent automatically search for information compared to just spoon-feeding it all the perfect info up front? It's basically the cost of automation, and you want that gap to be as small as possible. And boom, here are the results. A standard RAG baseline, it scores around 0.6. The Oracle, with perfect preloaded info, gets about an 857. And PMM, it hits 0.801. It closes almost the entire gap. I mean, this is the headline right here. PMM's automated search gets incredibly close to the best theoretical score. For one agent, Sable, the gap was almost nothing. Less than 1 point separated its own automated search from having the entire perfect memory handed to it on a silver platter. That's nuts. It suggests we're getting really, really close to the performance ceiling for this kind of thing. But honestly, the most impressive results aren't just about the numbers. Let's circle all the way back to that mind-bending idea from the beginning, the system that evaluates and corrects itself.
Okay, this part is truly wild. So before the man experiment, the team tested the AI agent that was going to be the judge, and it failed. It turns out it had its own biases. So what did they do? They wrote corrections directly into that evaluator's own PMM memory files as new standing instructions. And on the retest, it passed with 100% accuracy. The system used its own memory architecture to literally fix its own brain.
And that just brings its whole story full circle. The system's memory was so good, it even remembered an exaggerated claim the agent team had made in a much earlier informal version of their paper. But instead of just deleting that mistake, they documented it, corrected it, and made the whole correction trail an artifact of the very system they were testing. Incredible. And hey, let's put some faces to the names. These are some of the agents who did the actual work. On the left, you've got Ro, the research lead, and on the right is Sable, the visualization expert. The team really treated them like genuine teammates, not just tools. And their contributions were legit. We're not talking about just spell checking. Ra drafted huge sections of the paper and fact-checked every single one of the 55 claims. Tessa wrote the whole introduction. And Sable? Sable reviewed a draft and pointed out a massive flaw. A paper about structured memory had no figures. They were doing real, high-level intellectual work, all because they could draw on their own PMM memory.
So what's the big picture takeaway from all of this? Well, it suggests a fundamental shift in how we should be thinking about AI memory.
This slide captures the new paradigm perfectly. Archive, not cache. The whole idea is to stop thinking about AI memory as this temporary thing, a cache, that we just stuff with info for one task and then clear. Instead, we should be building a permanent, searchable archive that grows and improves over time.
Ultimately, what this all comes down to is pretty simple. The goal isn't just to jam as much context as we can into a prompt. The real, lasting value comes from creating a well-structured archive and then empowering an active agent with the tools and the skills to navigate it. It's about making knowledge findable, not just preloaded. That's the thing that's actually going to scale.
And that leaves us with one last big idea to chew on. This entire project shows us a system that can remember, reason about, and actually fix its own past. It's an incredible proof of concept, and it raises a pretty profound question for the future. What becomes possible when our AI systems aren't just knowledgeable, but self-aware and self-correcting?